Okay, let's start. We are in 2.1. We're talking about the determinant. Last time I mentioned some things, the fact that, let's recall some important facts. Only square matrices have determinants. So in fact, you can think of a determinant as a function from a set of square matrices to some field F such that the output is the signed volume of the parallelepiped. Formed by the row vectors. Last time you also saw that the determinant was also useful in solving equations. So there we also mentioned Cramer's rule. For n by n systems. That means A is an n by n matrix. Right? So if you have a system AX equals B, and if we set D to be the determinant of A, and we had another notation for that. We use absolute value bars, so we use absolute value bars for matrices, it means determinant. And set dxi to be the determinant of AXI. This is the matrix obtained by replacing the ith column of A with B. Then there were three situations. One, if D is not 0, the system has a unique solution. Given by, to solve for each variable, you just take the determinant of that matrix divided by the determinant of the coefficient matrix. 2. If D equals 0 and all the other guys also equals 0, then there are infinite solutions. And 3, if D equals 0, but some dxi not equals 0, then there are no solutions. By the way, we also spoke of a theorem last time that talks about these are really the only three situations that you can have for any linear system. You'll either have exactly one solution, no solution, or you'll have infinitely many. You can never have any in between or any other number of solutions. And Cramer's rule can actually tell you when each of these situations occur based on determinants in the event that you have a square system. So the number of rows and the number of variables are the same. Okay, so that's kind of where we picked up last time, but we didn't actually talk about how to actually find a determinant. So that's kind of where I want to start now. So computing determinants. So I'm going to give you a method, and the point of the method is to really capture the definition that we want to go for. So you really want to think of it as we're just using some sort of algorithm to get to the formula that will give us the volume. So you can compute the volumes for a bunch of parallelograms, see the pattern that's happening, and try to figure out some construction to get to that pattern. There are many constructions, but we're going to talk about one main one, which I think is the easiest to do by hand. The others usually would require some higher level mathematics. So there's a nice standalone formula that's attributed to Leibniz, but you actually need some abstract algebra, some knowledge of abstract algebra to use it. So we're going to use something that we know how to deal with it. So let's talk about computing determinants. There are many ways. Many constructions that can give us the pattern that we require. But we will look at the method of, it's called Laplacian Expansion. AKA Cofactor Expansion. So they both mean the same thing. Later, we will see how to use row operations to help us. So I'm going to show you how to compute determinants. The process can get quite annoying if your matrices are very big, and especially if you don't have a lot of zeros in your matrix. And so there will be ways you can kind of cut down on the work and make shortcuts, and row operations will actually provide one of the ways of shortening the amount of computations you have to do. So first I'm going to tell you the main method for finding the determinant. Then I'm going to show you some ways on how to make it easier to find determinants in multiple situations. And it turns out that just by the way we are constructing it, we'll be able to prove a lot of theorems about determinants and about matrices in general, and hence about the functions that they represent. So it's going to be very useful in the long run. So it's worth the effort. So first, let's actually do some definitions. And let me just mention that pretty much everything we're doing today, whether I state it or not, we're only working with square matrices today. Right? The determinant isn't defined otherwise. So if I write A, assume it's an n by n matrix. N rows, n columns. So let's actually go to some definitions. Definition. Let A be a matrix n by n. Its ijth minor is defined to be the determinant of the matrix obtained by eliminating the ith row and jth column. So I know we don't know what determinant is, but this is going to collapse on itself, and we'll end up being able to figure it out. So just take that as a definition for now. Because I'm going to write down a formula that gives you the determinant, but we're going to need to know the names of some of these things. So I think I have an example here. I sort of put a general example. Maybe I can do a specific one? I don't know. Do you guys want a general one or a specific one? So let's say A is A11, A12, A13, all the way down to A1n, A21, A22, A23, all the way down to A24, A31, A32, A33, A3n, A1, A2, all the way down to A and N. So this is an example. So let's say this is some random n by n matrix, then it's, and I'm going to define, let me give you some notation. The notation is Mij. So the ijth minor, we will call it Mij. So it's 2/3 minor is does anyone think they can read the definition to what the 2/3 minor is?
It would be the second row, third column.
So we're looking at the second row, third column. Again, it's the ijth, referring to the ith row and jth column. So what's in the second row, third column? This guy. Okay. Now, what is the minor supposed to be? You eliminate everything in that row and column. Right? And if those guys are eliminated, you have another matrix left over, right? You have this one, all the others. Everything except these guys, you kind of just erase this row and this column, and you're left over with a matrix. That new matrix, if you take its determinant, that is called the minor in the 2-3 minor. I think they usually put a little comma here. So this is just going to be the determinant. I remember the notation for determinant, you can use a straight bar. So that would be A11, A12. You would skip A13, so the next one would be A14, all the way down to A1n. You would not have the second row at all, so it would skip to the third row, A31, A32. A33 would be eliminated, so the next thing would be A34, all the way down to A3n. This goes all the way down to AN1, AN2. The third column is, so the next one here is to be AN4, all the way down to ANN, right? So in other words, the minor is a smaller matrix. It's a matrix that's exactly, if this is an n by n matrix, this will be an n minus 1 by an n minus 1, right? So if this was a 4 by 4, this guy would be a 3 by 3. If this was a 5 by 5, this guy would be a 4 by 4, and etc., right? It's breaking down by one dimension, right? The idea, of course, being is ultimately we're going to get to a point where we keep breaking down things into smaller matrices until we get to 2 by 2s where we actually know a formula for it to compute those. Yeah.
So say this was a bigger matrix, then would you keep breaking it down, like breaking down the minor?
Yeah, it's possible to now, if you take the minors of this guy, you can take now the minor of this matrix again, and you can break it down even
until
further.
it's like 2 by 2.
So the idea is you're going to break it down by 2 by 2. That ultimately that's where we're going.
And you would keep, as you keep breaking it down, you would keep going to the second row, third column of the next matrix.
No, not quite. This is just one example. I'm just giving you one minor. The method to compute determinant, we're going to be looking at multiple minors, and I'm going to tell you how to choose which ones you want to look at. Okay. This is just think of this as a definition. The definition of a determinant will involve this definition. well, it'll involve kind of this definition. There's one thing we're going to put on top of it. We're going to call it a cofactor, which is where the name cofactor expansion comes from. So let's define a cofactor. So A, n by n, is a matrix. Its ijth cofactor is defined by, this is the notation, Cij, and here's how it's defined. It's actually the minor, Mij, but it takes a sign, -1 to the I plus j. So depending on the location, I would actually take the negative of this guy or the positive of this guy. And that will be defined to be the cofactor. So in an example here, for the above, C23 or you can put a comment here if it's ever unclear, is going to be -1 to the 2 plus 3, which ends up being -1 times n23. Or in other words, here it would be the negative of n23. In other words, it would be the negative of that matrix I had here. Yes?
I don't get what you're actually doing to the system. Like, because this matrix represents a system of linear equations, so I don't get how you can just...
The coefficient matrix, yes.
Yeah, so I don't get how you can just, like, cross out basically an entire equation and an entire variable from the system, and the answer is still, like,
Well, I didn't really describe the process to you yet.
Okay.
I'm kind of, at the moment, describing the components that I'm going to put together into a process.
Okay.
So you might have remembered back in lecture 00 when I was talking about a 2x2 determinant, how we developed that formula, right? What we did was we were finding the areas. So there was a bunch of things. We were, in each case, we were multiplying two things, and then we were adding some of them and subtracting some of them because they were really areas, right? So it's kind of the same idea that's going to be happening here. We're kind of adding and subtracting certain areas. And so each of those components is going to be given by these guys. And we're going to add a bunch of them in a very systematic way to get to the volume. That's kind of the idea. So I'm really trying to describe here an algorithm to get to that formula, but we're just giving notations to each of the components in that algorithm. So I know it might seem very abstract at the moment, but it's really just an algorithmic way to obtain a volume formula, right? For something that's of general size. We want a general formula to describe volume. So yes. Personally, I hate memorizing formulas. So now when you give me a formula on top of a formula, I always like a mnemonic to make sure I remember the formula. And in practice, I think it's nice to know this mnemonic. And it's the following. Sign distribution will follow this pattern, right? So for a random matrix, the element here in the first row, first column will take a plus sign because this will be 1 plus 1 and it will be a positive 1. If you move over, you start to get a negative sign, then a plus sign, then a negative sign. The signs will alternate as you're moving. Same thing here, that would be a negative sign, a plus sign, a negative sign. The signs will alternate as you're moving. And so you sort of end up with this checkerboard pattern of signs, right? Where pluses and minuses are alternating as you move horizontally and vertically. So if you want to remember -1 to the I plus j, you can do that by all means, but personally I think visually speaking, it's nice to imagine this checkerboard that's imposed on top of your matrix. And the only way to remember it is to realize that the top left, it's always a plus in the top left. And then you alternate signs afterwards. did you have a question?
So this one would be a negative?
Yeah, so knowing how to, another way we could figure out that this had to be a negative is because if this is a positive, this would have to be a negative, positive, negative. Right, just by me following that pattern.
So why didn't that negate then? Because you said it depends on the sign.
It is a negative, there's a negative sign right here.
I mean, like, wouldn't it be positive then? Because you said the sign, like, whatever sign it is influences that.
Well, if this happens to be a negative number, if this matrix happens to be a negative number, yeah, you'll get a positive number. This is this sign has nothing to do with the numbers you see here. This is a sign that we're imposing on it. Right? I'm going to just take this expression and put a negative sign on it. Right? And I'm putting it on it according to this chart. What do we do next? Did I define it yet? Okay, so now with these things in mind, I can define a determinant. I think I told you everything you need to know to define it. With those ideas in mind, I can write down a very nice formula. The formula is nice if it can be very handy when you're proving things. In practice, if I'm giving you a matrix to find the determinant of, it will be small enough where you don't have to write out the formula. You can kind of do this method, which we'll go through an example of that as well. So here, Laplacian expansion. Method to find determinants. So given an n by n matrix A, choose any row or any column. One or the other. You can pick a row or pick a column. Not both. One or the other, right? Or. Exclusive or here. Right? So you're going to choose a row or a column, and I'm going to tell you ways in which you might want to do that. There are efficient things to choose and non-efficient things to choose. So you're given an n by n matrix, choose any row or column to expand along. And so you're talking about, I'm going to expand along this row or expand along this column. And you can choose any row or column, the definition will be the same. Say we chose the ith row, or the jth column. Right? And here I'm thinking of my matrix. I'm going to denote its entries by aij. Here, without further ado, finally, is the determinant. Then the determinant of A is equal to. So let's say I'm doing the ith row. Then the determinant will be equal to AI1 times CI1 plus AI2 times CI2 plus all the way down to AIN times CIN. So I'm going to take the elements along that row, and for each element in that row, I'm going to multiply it by its cofactor. And I do that for every element in that row. So that definition I had before, that computation thing that I had before, you're pretty much going to do this for every element in a row. Right? So you can write this as the determinant is just the sum, k goes from 1 to n, of aik, cik. Or, that's if we expand along the ith row. So that's what this if we expand along the ith row. Or we can also think of the determinant as A1j, C1j, plus A2j, C2j, all the way down to A and j, C and j. Or the summation from k goes from 1 to n of akj, ckj. If we expand along the jth column. I have a specific example here, but let me show you the idea with a generic example. So let's say I have a 3 by 3 matrix. So A is, let's do A, B, C, D, E, F, G, H, I. Now, in general, I can choose any row or any column to expand along. Let's expand along the top row. Right, so let's say I choose this row to expand along. Now, two things are going to come to play. You need to find all the cofactors. The cofactors would then bring a sign, right? So that means whatever answer you get here, you're going to apply a plus sign because it's at the top left, and you're going to alternate the signs. So you would apply a minus sign here, you apply a plus sign here. And here's how you're going. So these are all the elements in the row. So this would end up being plus A, and you're going to multiply that by the cofactor of A. Now the cofactor of A is the determinant of the matrix that you get when you block out its row and its column. Right? So you eliminate the row that A is in and eliminate the column that A is in, you're left over with the matrix E, F, H, I. And so you're going to multiply A by E, F, H, I, by the determinant of that. Now you go on to the next one, that's a minus. Minus B. You block out everyone in his row and his column. You end up with another matrix, D, F, G, I. You're going to multiply by the determinant of D, F, G, I. Then you move on to the next element in the row, that's C. Plus C. You're going to multiply by its cofactor. Eliminate everyone in its row and its column, and you would have D, E, G, H. So you multiply by that determinant. So now you see I had a 3 by 3 matrix and I wanted to find its determinant. Should be stating determinant here. And the determinant of a 3 by 3, I can look at it as a bunch of determinants of 2 by 2s with certain products in front of them. And I can then break this down even further, right? Because we actually know how to find the determinants of 2 by 2s, right? So I would multiply this by this times that by that. So this ends up being plus A EI minus FH minus B times DI minus FG plus C times DH minus EG. And to multiply that out, this is AEI minus AFH minus BDI plus BFG, big friendly giant, plus CDH minus CEG. Right? By doing that whole cross product thing, the cross multiplication thing that we saw last time. So it turns out this expression, and again, this will sort of fall in line. If you did this in 3 dimensions, this will sort of fall in line of you multiplying certain sides of that parallelogram and adding some areas and subtracting some areas, adding some volume and subtracting some volume to find the volume of the parallelogram or parallelepiped. Right? You might also remember this. This might remind you of taking a cross product in Calc 3. A cross product was in fact a determinant. They never told you that at the time. They just tell you how to do it for 3 by 3s. But it's a very general method. You can do it for 3 by 3s or anything larger, any other size. Technically you can even apply this method to 2x2s, but 2x2 we will use as the basis because we know how 2x2 determinants work. We derived that formula last time. So the idea is if you're given anything bigger, you use these methods to break down the matrices. So if I had a 4x4, I would get a bunch of 3x3s, and then those 3x3s, I'd break them all down to 2x2s, and then I can get to the determinant.
Wow.
And so it's going to be a very iterative process to break things down, right? So if you start with a 10x10, you have to break it down to a bunch of 9x9s, break down to a bunch of 8x8s, and you keep going until you get to 2x2s, and then you can finally say the answer.
On a
Right?
test,
So,
I'm gonna have 2x3s.
huh?
On a test, I'm gonna have like 3x3s.
Well, I'm going to give you guys, well, in general, I wouldn't put something pretty huge. I don't think I would go larger than maybe a 4x4 or 5x5. But in the event that I do venture off into larger than that, I am going to show you methods that can actually make this computation easier, right? For one, sometimes it might be easier than you would think, just by the numbers that are already given to you.
So if you have a 3x3, you would just multiply down all the numbers on that, like, because when you have a 2x2, you would say E times I. So
E
let's
times
say-
I minus F times H, yeah.
Right. So what I'm saying is, like, if you have a 3x3, you would do like E times I times F. Let's say, like, if you're going down and minus, then towards the other side.
There is a mnemonic for 3x3s. You have A, B, C, D, E, F, G, H, I. What you do is you can copy the first two columns here, and you can actually multiply it down across here. You'll notice that you get the E, A, E, I.
Right, okay.
So you'll add all the ones down here, and then you can multiply across up there, and you'll subtract all the ones up here, and you'll get that same thing. It turns out, though, that trick only works for 3x3s. So if you're in a 4x4, this actually won't work. So 3x3 is a very special case where that pattern happens to work out. But I would rather you memorize it this way, because this will work in all cases, any size. Okay. But of course, you can already appreciate that this can be quite annoying if you get big enough. So there are a couple ways to kind of shorten our calculation. So let's actually do some example. So we're going to do a 4x4. Now I know that sounds like it's going to be a lot, but I'm going to show you that it doesn't have to be a lot. Look at this guy. Find the determinant of A if A equals this matrix. Is that the one I meant? That's actually a little easier than I wanted it to be. Okay, 1, 0, 0, minus 1. 3, 1, 2, 2. 1, 0, minus 2. 2, 0, 0. So now, the important thing to remember here is, one, you have to check that it's a square matrix. A is square, check, which means I can't find the determinant. Second you need to know is that we can choose any row or column that we feel like. Right? So I know when you were doing cross products back in Calc 3, you literally always expanded along the top row. It was always I times this and J times that and K times this. But in general, it didn't matter which row or which column you chose. You can choose any one. So given the fact that you can choose any row or column, and you want to compute the determinant of this, which row or column would you choose? Second column is definitely the best choice. Right? Now, there are other tempting choices, I will admit. The first row looked pretty nice. It had 2 zeros in it. The last row also looked pretty nice. It had 2 zeros in it. But the second column actually has 3 zeros. So that's going to be very nice. Now, remember how we compute determinants. We're going to end up multiplying these numbers by cofactors. But if I multiply 0 by a cofactor, I don't have to compute that cofactor. So one important idea is, if you're computing a determinant by hand, choose the row or column with the most zeros. Right? It could make the difference between you being able to do the calculation in 1 line or 20. Okay? Choose the wrong one, you choose to expand along the second row, you'll be there for a very long time, because then you'd break it down into 4 3x3s, and then you might have to break each of those 3x3s down into 3 2x2s, and then so on and so forth, right? But choosing the second column actually makes this thing not so bad, okay? So choosing that, remember when we choose the column, there's a sign that we have to worry about. The signs always start as a plus at the top left. This is the minus 1 to the I plus j, which means this would take a negative sign because I'm alternating, which means this one would take a positive sign. This would take a negative sign, this would take a positive sign. So I just start at the top left, get to the row or column that I want to, and then I can fill out the signs according to the pattern. So now this is how the determinants would look. The determinant of A is going to be plus, well, minus. Let me just go through the motion so you can actually see how it would look. So I'm going to be writing in zeros even though it won't matter. So it's 0 times, block out its row and its column. So it's going to be 0 times the cofactor 3, 2, 2, 1 minus 2, 1, 2, 0, 1. Then plus 1 times, block out everyone in his row and his column. That's going to be 1, 0, minus 1, 1 minus 2, 1, 2, 0, 1. Minus 0 times, block out everyone in his row and his column. It's going to be 1, 0, minus 1, 3, 2, 2, 2, 0, 1. Then you go to the last guy in that column. Block out everyone in his row and his column, so that's going to be plus 0 times 1, 3, 1, 0, 2, minus 2, minus 1, 2. So I broke this this 4x4 down into 4 3x3 determinants. But of course, the nice thing is 0 times the determinant, right? It's going to be 0. 0 times the volume is 0. So really, I only have to compute 1 3x3 for this guy. Okay, so this guy is actually equal to just this. Now, how do I find that? Do it again, basically. So what would you choose here?
Second column.
Again, the second column. It happens to have the most zeros again, right? The first row and the last row actually has 1 0, but the second column has 2 zeros. That's even better. So again, I'm going to do that sign. This is a plus, minus, plus, minus. So this is going to break down into minus 0 times, block out everyone in his row and his column, 1, 1, 2, 1, plus a minus 2 times, block out everyone in that row and that column, 1 minus 1, 2, 1, minus 0 times, block out everyone in that row and that column, 1 minus 1, 1. These are of course zeros. And now we get to a 2 by 2. We know how to do the 2 by 2s. We do that cross multiplication thing. And so this ends up being minus 2 times 1 plus 2. In other words, that's minus 6. So minus 6 is the determinant of that matrix.
I have a question.
Yes.
So say we have a matrix like that's like 3 by 3 or 4 by 4. To find the inverse, would we find the determinant and do 1 over that determinant and then multiply by the matrix
No.
using this?
But we didn't,
Oh.
we haven't talked about inverses yet. I kind of spoke about the general idea, but we'll talk about inverses later. For now, we're doing determinants first. There's a method that that you can find the inverse. There are ways to get to the inverse using the determinant. There are also ways to get to it without using the determinant. I'll show you two ways to get to the inverse of a matrix. One with the determinant, one without it. And it'll kind of be a personal choice after that one. So yeah, the determinant of this matrix is -6. Now there are a bunch of ways you can think about that. One, if this guy represented the coefficient matrix for a system, then the x, w, x, y, z, to compute those guys, I would be dividing whatever number by -6 is one way you can interpret it. You can also interpret it as, in 4 dimensions, the volume of this parallelepiped is 6, whatever that would kind of be in 4 dimensions. But that's how you compute a determinant, right? So you kind of break it down. So it has to start out being a square, choose any row or column to expand along, follow the checkerboard of signs, and then you compute the cofactors times each element in that row or column. And the idea being is you're breaking it down in size until you get to a point where you actually know how to get to the answer.
Professor, what are the positives?
Uh,
Because you have 2 times -1 inside the 2 by 2, and then the -2 outside.
No, it's 1 times 1 minus 2 times minus 1.
Oh, sorry.
There's a minus. So it's this times this minus that times that. Yeah.
What is the significance of the determinant being negative?
It would have consequences in terms of solving equations. But beyond that, there are a few consequences, but nothing we need to worry about at this point. Yeah. It's more important for this class to worry about whether it's 0 or not 0. That's where things are going to get interesting. Yeah.
Well, let's hope the 3 by 3 in the other way you showed us. I got 6, like positives. Like, you know when you write the 2 columns, you copy them again?
Yeah.
When I did that, it was positives.
No, you should get the same thing. Let's do this quickly. 1, 0, 0. I wouldn't recommend you do the.
No,
Oh,
like from
what?
there, like 3 by 3.
Oh, at this point, yeah, because you can't even do it there.
Yeah.
I think you did the same mistake I did.
Like that. You copy down the first 2 columns. And then you multiply down. So this will give you a -2. Multiply down. This will give you a +0. Multiply down. This will give you a +0. Multiply up. That will give you what? A +4. But you're subtracting it. Multiply up. That gives you a -0. Multiply up. That gives you a -0. So you end up with -2, -4. Yeah. Okay. What next? So that's how to compute a determinant. Let me talk about.
Can I ask you one question?
Yeah.
What would happen if you use the constant and you multiply it directly in your with your factor directly without, let's say you calculate the absolute value and you just multiply directly within the absolute value and then you cross multiply. Does that work? Is that what I mean?
I'm not sure what you mean. Like if you start here, what are you saying?
No, no.
If you,
Right, you can -2. No, the next step. Right. So we are left with just one expression, right?
Yes.
Right. If instead of breaking it down further, you got -2 times 1 is -2, and you do that for each element within.
So distributing the 2.
Right, just distributing.
And then,
just.
Oh,
cross multiply,
distributing the
right,
2 and then.
before multiplying.
That would actually be different.
That's it.
Yeah. We'll talk about that. That's in the next section. There are going to be,
Yeah.
we're going to study how row operations affect determinants, and it turns out if you multiply a matrix by, each row of a matrix by a number, it changes the determinant.
Mhm.
So bringing that 2 inside and multiplying all the rows by 2s, it actually will change the answer.
Yeah, like
It would mean something different. It's kind of like, and using the interpretation that we have of volume, that would kind of make sense. There's a difference between saying, I'm doubling the volume of this thing, as opposed to, I'm doubling the length of each side of this thing and then computing the volume. It'll actually increase by different magnitudes. Yeah. So if you look at think of the volume interpretation, you'd realize that that also kind of would change things.
All right.
Right. So doubling a volume and lengthening each side by a factor, they're two different things. They give you two different answers.
All right.
And the definition of our determinant will include that. Like we can actually prove that using the definition. That if I multiply a row by a constant, my determinant will be scaled by that constant in some predictable way. So yeah, don't multiply in. Just keep breaking the determinants down. Don't expand a number into a determinant. It changes the answer. Yeah, so you can't think of this as parentheses or an absolute value. It means something else. If that's the question. I think that's probably the confusion. Don't think of it as like an absolute value. Because that's actually true for absolute values. You can actually multiply a number inside. Yeah.
I'm sorry, I may have skipped over this, but what is the determinant of a 1-by-1 matrix? Is it the entry itself?
It's just the entry itself. Yeah. So again, going by the volume interpretation, that's kind of like you asking, what is the length of a line whose length is 6? It's kind of, you know, so if you're in a one-dimensional thing, you know, that just means, oh, it's one-dimensional and the length is 6. Right? Once you go to 2-by-2s, now you're in 2 dimensions and you're looking at a parallelogram, and then it bumps up from there. So the determinant of a 1-by-1 matrix is literally itself, because, yeah, so you would take, that would get the plus sign and then its cofactors, nothing. Okay, so let's go. Let's talk about certain matrices and finding their determinants. So some matrices have nice patterns that we can take advantage of. So let's look at a definition here. Let A n by n be a matrix. Then A is called upper triangular. If all entries below its diagonal are 0. So basically that's a matrix that looks like, here's the main diagonal. There can be any numbers here, and these can be any numbers, but you have to have all zeros down here. Right? That's called an upper triangular. So the non-zero numbers only are entered in this upper triangle, but there's zeros everywhere below that triangle. Another definition is A is called lower triangular. If all entries above its main diagonal are 0. So that would be, you know, a matrix where here's its main diagonal. You can have any numbers here being populated down here, but above that main diagonal you have all zeros. That's called a lower triangular matrix. Fact. Would it count as a theorem? It's not really a theorem. I mean, it's just it's a computational fact. If A is triangular, then the determinant of A is, you guys think you can figure it out based on definition? I know it's kind of put it on the spot. Yeah?
I think it's going to be 1.
1? Like it's always going to be 1?
Yeah, because if you go down the diagonal, always pick the first O, because they're not necessarily one.
They're not necessarily one. Huh? The product of the main diagonal elements. The proof, keep expanding along the first column. Right? So the idea is you'll start here and then you'll break it down. You'll eliminate everyone there. But then everyone else here is 0, so choosing the first column of the new one would give you 0 everywhere else, and you do his determinant. Then you start doing that. So you keep going down in steps, but you keep choosing the first column because the first column will always have the most zeros. At the end of the day, you get to a point where there are no more zeros to choose, and your determinant just ends up being this times this times this times this times. I'm not going to write that out, but you can write that out, but that's the idea. Keep expanding along the first column. You'll end up with it's just the product of the diagonal entries. Corollary to this fact, I can never remember how to spell the word corollary, so I'll just see it. Corollary is just a fancy word for a consequence. So the determinant of the identity matrix, the n by n identity, is?
That's 1.
That's 1, because this guy is triangular. This is upper triangle.
Or lower triangle.
It's also lower triangular, yeah. So it's triangular. That's an important fact. We're going to be using that, and it follows straight from the definition from cofactor expansion. So the determinant of an identity matrix is always 1. Yes. It also means the determinant of any diagonal matrix. This will still be true. The determinant of A equals product of diagonal entries. If A is a diagonal matrix. Because it would be both upper and lower triangle.
Well, yeah, but I mean, does it need to be said that if any of the main diagonal entries are 0, then the thing is also 0?
No. No, because that would follow from this definition. In the product, you'll have a 0 entry, and you're just killing it. Here's another fact. The determinant of a matrix is actually equal to the determinant of its transpose. You guys remember what A transpose is? When we interchange rows and columns. Proof for this, expanding along the ith row of A is the same, it's exactly the same as expanding along the ith column of B. Because in this one, all the rows here become the columns there. So expanding along a row here is literally equivalent to expanding along a row there, and all the numbers would be, in relatively speaking, the exact same positions. You'll get the same computation at the end of the day. So a determinant of a matrix and a determinant of its transpose, it's always going to be the same. example here for the triangular matrix. Yeah, let's write it out. Example. Find the determinant. So this is one case in which I wouldn't really feel bad putting something really large on an exam. So if I say about the determinant of this, 5, 0, 1, 2, 7, 0, 2, 0, 3, 4, 0, 7. So something like that, if I actually define the determinant, sure, oh my god, it's a 5 by 5, but it's upper triangle, is the idea. So if you wanted to find that, just realize that that's the main diagonal. Literally everyone below that is 0. So the determinant is literally just multiplying these numbers. The other numbers don't even matter, you ignore them. So that would just be equal to 5 times 2 times 1 times minus 1 times 3, which is 30. Negative 30. This is a minus 1. So really, those are some easy cases. I mean, the example I gave you had a lot of zeros in one of the columns. And of course, with upper triangular, there are a lot of zeros all over the place. Sure, these guys are easy to find determinants, but what about something more general? So we're going to actually move on to the next section. So 2.1 was just showing you how to find a determinant, so we've covered that. So we're going to 2.2. Because I'm changing the order of the textbooks, I might mention some things from 2.3 as well. So this is, we're going to look more at evaluating determinants. But now I'm going to using row reduction. And also how row operations affect determinants. So we'll spend about 3 sections on determinants, but it's an important idea to know about, right? Because it's actually insanely useful. It's amazing how many ways that finding determinants are useful. So we want to know how to compute them very efficiently. And of course, in real life, you're never going to have to actually find a determinant by hand, especially if you have a large matrix. But even computers, if you want to program computers to actually use linear algebra, it's good to program it ways for it to cut down computation, because computation can really build up, you know. So if the chances are, if you're using a computer to do linear algebra, the matrices would be like thousands of rows and thousands of columns, and then you're breaking these down to thousands of determinants. It's nice if the computer can just like take a shortcut, because you know computation time compounds, the memory's going to run out after a while, things like that. So it's good to know, hey computer, you can do this as a shortcut. You know, so it's nice to know shortcuts for stuff, even if you're not going to be doing them by hand. So it turns out we can actually use row reduction to actually reduce computations from doing determinants. But slightly before that, we want to know how doing a row operation will affect doing the determinant. So that's what we're going to talk about first, and then I can tell you how we can use them to help us. So let's see which theorem I talk about first. Let's I'm going to state 2 facts without proof. Not because the proof is difficult necessarily, but it's really it would be really long to write it out properly. So lemma. That's a fancy phrase for a theorem. Is this really groundbreaking mathematical fact? You call it a theorem. Any fact that you use to support the proof of a theorem, you call it a lemma. Anything that's a consequence of an important theorem, you call it a corollary. It's just some mathematical vocabulary. Okay, let's move on. So I'm going to talk about two lemmas. Here's one lemma, a matrix with two identical rows or columns has determinant 0. It's a very simple fact, but to actually write it out properly is going to take a while. I can tell you how you would prove it. Basically, you start by a 2 by 2. It's very easy to see that this is true for a 2 by 2, right? So if I have a 2 by 2, and that's just like A, B, A, B, so you would start here. Then what is the determinant going to be? The determinant of that is going to be AB minus AB. So that equals 0. So it turns out to do with the other cases, you really do induction. Right? So then you're going to have to write out a matrix in general, and assuming that it works for a 2 by 2, then you're going to use cofactor expansion to break it down and show that eventually you break it down to a bunch of 2 by 2s where each of them will be 0. So to write that out is going to really take a long time, and I kind of don't want to do it. So, but that's it. It's straightforward, but it's very long, and you have to be careful to be technically correct. But you basically, it's clear for a 2 by 2. Use induction to prove it for larger, right? So assume A has n rows. The base case is n equals 2. Then use induction to prove it for larger, and induction will show that it will work for any size. So we spoke about induction already. So that's just a fact. A corollary from this fact is the fact that if a matrix has two proportional rows or columns, then its determinant is 0. Right? So it's not necessarily if they're identical. So in the 2 by 2 example, this would be a matrix that looks like A, B, and this is something like A times some scalar k, and this is B times some scalar k. So if you have two proportional rows where one row is just a multiple of another row, the determinant is also 0. The proof for that would be, you would use this. You'll expand along one of those rows, and you'll realize that all the cofactors that you get will have two identical rows remaining. And so So I won't give you the proof. They're fairly straightforward, but it would be really long to write out. I wouldn't really ask you to prove that either. But with that, there is another important theorem that we can get from that. Jeez, I want to. Here's another lemma. Let A, B, C be matrices so that they are all the same except in one row and in that row the entries of C are the sum of the entries in A and B. Then turns out that the determinant of C will be equal to the determinant of A plus the determinant of B. Okay. And so I'm saying A, B, and C are exactly the same except for one row. So let's say my C is equal to, and this is just an illustration. It's a very specific example. So something like, let me first do my A. So my A is A, B, C, my B is E, F, G, but these they're exactly the same numbers. It's completely the same except for this one row. And it turns out C is it's completely the same except for that one row as well. However, it's the case that that row is the sum of those other two. That's A plus E, B plus F, and C plus G. Then it turns out taking the determinant of this matrix is the same as taking the determinant of those two and adding them together. And with these two facts here and this fact here, I'd be able to tell you how each individual row operation will affect the determinant. So remember, there are three types of row operations that we have. You can swap two rows, you can multiply a row by a non-zero constant, and you can change one row by adding to it a multiple of another row. So there are three things you can do with the row operations. And with these three facts, the ones that I just erased, and this one, I'll be able to tell you exactly how doing each one of those things will affect the determinant. Can I prove this quickly? But that's of course for next class, but maybe we can look at this one. Let's just do an illustration. Of course, the more general case, you'd have to like write out dot, dot, dot. Let's say proof, let's do a 3 by 3 case. And of course, the general proof with you be writing ellipses of everything. Okay, so let's just do the 3 by 3 case so that we can get out of here quickly. So let's say A is A, B, C, D, E, F, G, H, I. My B is J, K, L, but everything else is the same. So we're going to say W log, suppose they differ in the first row. W log means without loss of generality. So it means the proof would be exactly the same if I had picked arbitrarily another row. Which I'll probably mention that a little later, but we're kind of out of time at the moment. And so C would be the matrix A plus J, B plus K, C plus L, D, E, F, G, H, I. And so now let's look at the determinant of C. And so now I'm going to do Laplacian expansion. I'm going to do it along the first column. So this is just taking on a plus sign, that's taking on a minus sign, that's taking on a plus sign. So let's actually look at what that would look like. So this would be A plus J times the matrix I get when I expand this, eliminate that row and that column, minus B plus K times the matrix I get when I get rid of that row and that column, plus C plus L times the matrix I get when I get rid of that row and that column. So I'm going to, remember, a determinant ends up being just a number, right? So I can expand parentheses here. So I can look at this as A times E, F, H, I, minus B times D, F, G, I. I can't bring the numbers inside, but I can actually multiply out here. Plus C times D, E, G, H. Right, so I just take the A times this, the B times this, the C times that, and then I'm going to plus the J times this, minus the K times this, plus the L times this. And you'll notice that this guy here, what is that? That's the determinant of this guy. Plus this ends up being the determinant of B. So next time I will use this fact to show you how a type 3 operation affects the determinant. And I'll show you about type 1 and type 2 as well. But this is an important fact to show you how type 3s will affect determinants. And we'll end there. So see you guys next class.